Hey, welcome back. This is now 6.2, and we're going to talk a little bit about growth and decay with exponential equations and a little bit of differential equations. So a differential equation is basically just an equation where you're solving for a function. So a differential equation it'll be I mean, literally anything that you've already kind of solved with an integral is a differential equation. So for example, y prime equaling 2x, that thing there is a differential equation. And to get the answer, you're looking for a function y such that when you take its derivative, you get 2x. So in particular, a solution would be x squared. But then there's other solutions like x squared plus 1, x squared plus 2, so you put x squared plus c. And that process you have of doing an integral is basically solving a differential equation. Okay? So you'll see it written like that, but you'll also see it written dy over dx equals 2x. So instead of writing y prime, you can write dy over dx. You can also throw in higher order derivatives. So you can have equations like y triple prime plus y double prime plus y prime plus y equals sine of x. Okay. And you're looking for the function such that when I add it to its derivatives, you end up with sine of x if it even exists. Okay. So 9 times out of 10, you could do that just for us by integration. You have to take a special class to kind of learn all the little techniques for higher order differential equations with more and more derivatives and that sort of thing. But in particular, what we want to look at are kind of the most generic forms, the exponential types. And yeah, so to begin this, what we need to be able to do is to solve some basic differential equations. And the method that we kind of show you is called separation of variables. And there's some little technicalities involved, but let's kind of queue up the homework and see how that goes. Okay, okay, so we'll start you easy with problem 1. There we go. Okay, so I have dy all over dx equals 28 minus y. So the objective is to get any variable with a y on the left and any variable with an x on the right. So here I'm going to multiply both sides by dx. So you just pretend the dx is a variable onto its own. And then I need to get this y expression here, this binomial thing, to the other side with all the rest of the y material. So I'm going to divide both sides by it. I end up with dy all over 28 minus y equals dx. Then to solve for the function y, what we need to do is integrate on both sides. Okay, so on the left side, we're integrating with respect to y. On the right side, we're integrating with respect to x. Okay. Just a note here on the left, because I put dy in the numerator, it's not really anything new. It's basically the, you can kind of move the dy around. You never want to have it in front of anything, but you can always think of, rather than writing 1 over 28 minus y times dy, you could put that dy into the numerator and save yourself a little bit of room. Just apply what the book is doing there. Okay? Okay, so hopefully no mysteries there. All right. Then I integrate on both sides. On the left side, I'm going to have to do a u sub for the denominator. It's going to be a natural log of some sort. The differential du will be negative 1 dy. And then I solve for dy. That will just be negative du. Okay. Okay, so on the left side here, I'm going to replace dy with negative du. And the denominator have a u. On the right, the integral of dx, if you recall, that's just 1, the integral of 1. Okay, so the integral of 1 is just x. And then we always put the plus c portion on the right side. Okay, technically it's on the left too, but we just add it to both sides and kind of combine the constant material into one constant. And working with these constants, it is a bit odd at first, but you'll get the hang of it. Okay? So the constants will absorb any other constants. So if you have like 3 times c, you can just replace it with a c. It's a bit odd, but you'll get used to it. Okay, so anyways, on the left now, I can factor out a negative. If you want to rewrite it to make it look more familiar, 1 over u du, it's just a natural log. And on the right, I'm just going to keep it as is. Okay, so I'm going to end up with negative ln negative ln of the absolute value of u. And on the right, I have the x plus c. And then rather than, so what I want to do is, well, you have to back sub first. So let me back sub. Okay, now I want to solve for y if possible. So sometimes you'll end up with what's called an implicit solution, where you can't get y all by itself. But usually you want y equals something, because that's what we're used to dealing with, right? We want an explicit solution, is what they're going to be called. In order to pull that off, I'm going to move that negative to the other side. You usually want all constants on the right. Okay? It's just going to save me a little bit of trouble in the long run. So I'm going to multiply both sides by a negative 1. So I'll have ln of the absolute value of 28 minus y. And I'll show you here in a second why I didn't want to just do it the other way. Okay. So on the other side I have negative x. And then technically it's minus c. But you can always just write plus c, because it doesn't really matter if it's negative or positive. Okay? And it's like what I was saying before, it absorbs all constants. Okay, the software isn't going to care. You put minus c, it won't make a difference. But you should really just think of it as absorbing anything you multiply by it, and it's just always going to stay at plus c. Okay, so now I'm going to exponentiate both sides in order to get that y out of the natural log. So on the left, I'll have the absolute value of 28 minus y. On the right, it'll be e to the negative x plus c. But I'm going to kind of break that apart and write it as the product, e to the negative x times e to the c. Okay. Now you can drop the absolute value symbols and replace it with a plus or minus on the right side. And I'm going to change the order of the factors. Okay. And now another kind of weird thing, I'm going to replace this whole guy here with a constant. Okay. What's going on right now is it's kind of encoded all the little steps that we've done. But at the end of the day, this thing in the red box will just be determined by x and y. So I don't need to have this record of where I've come from. Okay, you could just replace it with a big C. Okay, so I'll have 28 minus y equals big C e to the negative x. Now I'm going to solve for y. So I'm going to move the y to the right-hand side, move the c to the e to negative x to the left, and flip-flop sides. Okay, and that's a fine answer, but you're supposed to always let the constant absorb the other constants. So let's rewrite this as 28 plus c e to the negative x. In the homework, it's not going to matter if you put a minus or a plus in front of it, but just in general, the way we write it, we let the constant absorb that negative. Okay? And that will be your solution to the differential equation. So now kind of scooching back here, let's see what would happen if I would have just left that negative there. Okay? So instead, let's say I decided to go ahead, well, maybe right here, and exponentiate. So I'd have e to the negative ln absolute value 28 minus y equals e to the x plus c. Okay, so on the left, you can no longer just do the cancellation equations with the e and the ln being inverses. You need to move that negative 1 inside the natural log. So already you have a little extra work. I'm going to go ahead and chop this up, and the e to the x times e to the c. Then the e and the ln's will cancel each other out, and you have 28 minus y to the negative 1 equals e to the x times e to the c. The negative 1 exponent is going to drop that expression into the denominator. And then to get y out of the denominator, you can cross multiply, or you can divide, multiply both sides by the 28 minus y, divide both sides by e to the x, e to the c. Okay. This thing on the left, you could really write as 1 over e to the x times 1 all over e to the c. Maybe you can see where I'm headed here. I'm going to flip-flop sides. 1 over e to the x is e to the negative x, and then 1 over e to the c, I'll just write it like that. And then I could drop the absolute values. I have 28 minus y equals plus or minus 1 all over e to the c times e to the negative x. And then I'm going to replace that critter with a big C, like that. And now we are in this position here. So a good rule of thumb is to always push any constant that you can factor out of an integral to the right-hand side. Otherwise, you typically will end up with these scenarios where you give yourself about 3 extra lines of work. In this case, maybe like 4 or 5 extra lines of work. Okay. All right, let's look at the next one, number 2. Y prime is 20 square root of x times y. Okay, so I'm going to rewrite the y prime as dy over dx and then separate. So get all the x stuff on one side, all the y stuff on the other. So leave the 20 on the right side. So again, leave constants on the right. Otherwise, you get yourself into a headache. And it's not a bad idea to just experiment once in a while with, going in the wrong direction. That'll teach you not to go that way anymore. But it could cost you a lot of time, right? Sometimes it's better not to learn the hard way. Anyways, we're going to divide both sides by y, multiply both sides by dx. Integrate on both sides. So on the left here, it's just ln absolute value y. On the right, you can factor out the 20, rewrite the square root as a fraction exponent to do a power rule. One half plus 1 is the same as 1/2 plus 2/2, which is 3/2. Divided by 3/2 is the same as multiplying by 2/3. And we always tack the constant onto the right-hand side. Okay, so here's an implicit solution. We want the explicit solution, so we're going to exponentiate to unlock the y from the natural log. So now I have the absolute value of y equals e to the 40 thirds x to the 3 halves times e to the c. Drop the absolute values, put a plus or minus on the other side, flip-flop the factors. Replace that big ugly plus minus e to the c with a c. Okay. And then we have a final answer. So again, the thing in the blue is just going to be some number. And what number is it? Well, it'll be determined by whatever the heck the x and the y terms are. Okay. So there's no reason to have this big ugly plus minus e to the c when all you really are doing is plopping in y and x and solving for that thing in the blue. Okay. You'll see that once we do particular solutions. Let's see if I can find one like number 5. So let's try number 5 and kind of see what's going on when we do actually look for a particular solution to the differential equation. Okay, so this equation is good because it is the form for the exponential growth curve. So the way it works is always going to be the rate of change of the population, which is that dy over dt thing, is proportional to the population. Okay, so the idea is if you have maybe a petri dish full of bacteria, if you have more bacteria, you're going to have a higher rate of change of a population, okay, of the bacteria. So if you only had 2 bacteria sitting there, they're not going to reproduce very fast. But if you have 1 million bacteria sitting there, they will reproduce very, very fast. There's also this idea of exponential growth versus exponential decay. So the bacteria case would be exponential growth. If you had something like radioactive material, you're going to be looking at exponential decay. Right? But anyways, getting back to problem 5, and what we're working with here is looking for a solution, but not just any solution. We want a particular solution that goes through the point 0, 3. Okay. So whenever you see that C value in front of your answer, that really represents a family of curves. And you can go through and plot a whole bunch of them in Desmos and kind of see what you're dealing with. Well, one thing at a time, right? Okay, so the first thing we want to do is separate. So I'll move the y over. You're leaving any constant on the right. So I'll leave the -1/2 there, move the dt over. Integrate both sides. You can factor out the -1/2, so let's just do that. The integral of 1 dt is just t, and then we always tack the c on here. Then I can exponentiate. Drop the absolute value, replace plus minus, rewrite the e to the c in front. And then you could replace this with just a capital C. Okay. So the deal is, in order to figure out what that C or what the thing in the box was, you just plop in the initial condition 0, 3. In either case, if you used either equation, you're going to get the same answer, right? But let's put it in the second one. Okay, so 0, 3 in there. 3 is the y, and 0 is the t. So I have 3 equals 0. E to the 0 is just 1. So C is 3. So my particular solution, y equals 3e to the negative 1/2 t. Okay, let's just to convince you that they both work the same. Let's go ahead and take this guy and plop him in here and see what happens, right? So I'd have 3 equals, and it has to be the plus version in this case. There's no way to have a minus result in a positive 3. Okay, so it has to be the plus e to the c, and then e to the negative 1/2 times 0. And so I have 3 equals e to the c times e to the 0. And then to get the c value, you have to take the natural log on both sides. So I have the ln of 3 equals ln of e. You could bring down the c using the power rule, and then the ln of e is just 1. So c is ln 3, and then plopping that into this equation now, I get y equals e to the ln of 3, e to the negative 1/2 t. Okay? And then e to the ln of 3 is just 3. So you just get the same answer. Right? But our idea of replacing that entire thing with just a constant c is much easier to work with. You don't have to kind of work with natural logs and all the exponential stuff. No. And what it comes down to is basically that thing in the box is just going to be some number, right? This guy right here is just some number, and it's determined by the ordered pair that's given, the initial condition. The actual solution to if I wanted to graph this thing right here, it's going to be a family of curves in the plane. It's not what you're used to, right? It's not just like a one particular curve in the plane. It's not just going to be this, or rather something like this. That's not what that thing represents. That thing in the box, y equals c e to the negative 1/2, is a family of curves. Okay? It's a whole bunch of these things. And then when they give you an initial condition, such as 0, 3, you're basically looking for the particular curve that goes through that coordinate. Okay. Let's get back to let's go and look more at some of these application type problems. We have to know how to translate phrases like proportionality. And you see that in problem number 6. You'll see it in the homework if you get ambitious enough to do the homework. So you see these sentences that you translate straight into differential equations. The rate of n is proportional to n. So problem 21 from the book. The rate of change of n, so that's dn over dt, is proportional. So you write equals, and then you have k is proportional to what? To n. So k times n. So there's all kinds of these proportionality statements that you can always look up on the web. So what does inversely proportional mean? What proportional to the square root of blah, 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 all that stuff. I don't think they get too carried away with it. Every once in a while you'll see it pop up. But anyways, the rate of change of n is proportional to n. That's this differential equation. That will resolve in one of our exponential expressions. Then they give you a bunch of initial conditions. T equals 0 when big N equals 250. T equals 1, then big N is 400. And they want to know the value of n when t is 4. Okay, so first off, I'm going to solve that differential equation. So I separate variables. I'm going to divide both sides by big N, multiply both sides by dt, leave the constant on the right. Then I'm going to integrate both sides. That k is a constant. You can pull it out of the integral, believe it or not. Integral of 1 dt is t. Then you can exponentiate both sides. Drop the absolute values. And replace. So this expression, or rather this equation, has 1, 2, 3, 4 variables. Right? And so what we're going to have to do is use these initial conditions in order to solve out for the sort of required variables in order to get to the final answer. So instead of x's and y's, we have n's and t's, and so the true unknowns are the c and the k. That's kind of what we want to figure out. Okay, so I just use these initial conditions. So I'll plug in 250, 0 for n and t. So 250, n is 250 when t is 0. K times 0 is just 0, so 250 equals c. And that'll allow me now to rewrite my equation as n equals 250 times e to the kt. Okay, so I use the first initial condition. Now go to the second initial condition. So n is 400. When t is 1, that's going to allow me to solve for k. All right, so I'm going to divide both sides by 250. It should be 40 over 25, so 8 over 5. Then take the log on both sides. And you get k equals ln of 8/5. So my equation n is 250 e to the t times ln of 8/5. And now you can use that equation to solve out for any other unknown. Okay, so in particular, I want to find n when t is 4. So in that case, n will be 250 e to the 4 ln of 8/5. So I'll go to Wolfram. And I'm getting 1638.4. Let's make sure did we get the answers? 8192 over 5. Yeah. Okay. So that problem then is similar to number 6. In number 6, they don't really tell you how many decimals. So in those cases, you just put in the answer kind of in its logarithmic form, which is what I did here. And I just put the thing in red into the answer box. Of course, this answer is different. They got different numbers. But all right. Then we kind of get into more of the land of pre-calculus with some of these exponential decay problems. Let's try number 8. So it's kind of a half-life problem. They're working with some sort of isotope. They tell you the half-life. is 24,100. The initial quantity, they don't know. I'll just write that as I sub 0. The amount after 1,000 years, you don't know. And they give you the amount after 16,000 years is equal to 1.5. Okay, so these problems work a lot like this previous problem, 21, and that they kind of give you some information and you have to solve for C and K and then use that new equation to solve for the information. Okay, so the kind of new piece is that half-life, and all that means, and now you don't have to really start with the differential equation. You can just cut to the chase, and you know you're going to be working with y equals c e to the kt. Right? Okay, so the kind of new part is this half-life idea, and all it says is that after 24,100 years, so t in that case is 24,100, after that time, y will equal 1/2 of the initial amount. And the initial amount is going to be that c variable. Okay, so plug that into the equation just like you were doing in the previous problem. So instead of writing y, I write 1/2 c. And that equals c e to the k times 24,100. And then we could use this to solve for k. Right? So I'm going to divide both sides by c. Get 1/2 equals e to the 24,100k. Take the natural log on both sides. Divide by 24,100. And I've solved now for this k variable. Right? So I can rewrite my equation. All right, now I go to the other bit of information they give me and plug that in. Right, so that's saying that t is 16,000. When t is 16,000, y will equal 1.5. So you just plug it into your equation. 1.5 equals c e to the 16,000 ln of 1/2 all over 24,100. Then you could solve for c by dividing. So c will be 1.5 all over e to the, this is a bit obnoxious, 16,000 ln of 1/2 all over 24,100. Okay, I'm going to get an approximation for that thing, so I believe that that's kind of what they expect in the homework. They want 3 decimal places. Okay, so I'll just go to my whatever your calculator is. I prefer Desmos. I actually prefer just writing it in normal. Looks like I'm getting 149 point. Oh, crud. You gotta be kidding me. I mean, really? Oh, now I'm getting a different answer. That's kind of concerning. This 2.3. Let me push enter so it doesn't go away again. 2.377. I must have forgot to put some parentheses in the first time. Okay, so now that I got the C value, which is the initial amount, so you can come up here and fill in that blank, 2.7 versus 2.377. I can also rewrite now my equation. So y will be equal to 2.377 e to the t times ln of 1/2 divided by the 24,100. And to get the final answer, I'm going to substitute in 1,000. Okay, so let t equal 1,000, and y will be 2.377 e to the 1,000 times ln of 1/2 all over 24,100. So 2.377 e to the 1,000 times ln of 1/2 divided by 24,100 in parentheses 2.310. And then you put that into this spot. Yeah, okay. So that's the exponential decay problem. Just by the way, exponential decay is going to happen usually when that constant y equals c e to the kt, when k is less than 0, you'll have decay. All right? And then when k is greater than 0, you'll have exponential growth, and it'll look like that. Okay. But anyways, so this was an exponential decay problem. For growth problems, usually we'll talk about compound interest. And let's look at one of those. Let's see if there's one in the homework. Yeah, sure. Okay, so problem 10. And instead of sort of an initial amount of like grams of some sort of isotope, you'll have an initial investment. So again, I'll call that I sub 0. And our initial investment for this problem is $14,500. You'll have an annual rate, so that'll be interest. You'll have a doubling time instead of a half-life. And then you'll have an amount after 9 years, or after a certain number of years. In this case, they want to give you 9 years, I believe. Yeah, so amount after 9 years. And, you know, really it's the same kind of problem as what we had previously, where you're kind of working with a given equation, in this case y equals c e to the kt. You want to figure out what the heck is c, what the heck is k, and then figure out the unknown information. Okay. All right. So in this case, they're giving you the initial amount, which is the c value. So good. For free, you automatically get the c value, which is 14,500. We need to figure out then the k value, and we could start. So we've already used I sub 0. We want to use doubling time. All right, so instead of half-life, the doubling time says that in 18 years, so when t is equal to 18, the y value will be twice the initial amount. So in our case, that would be twice the $14,500. All right, so after you kind of wrap your brain around that, you just substitute it into the equation itself. So you have 2 times 14,500 for y equals 14,500 e to the kt, and t is 18. Divide both sides by 14,500. Natural log it. Solve for k. So your equation for this investment is 14,500 e to the t ln 2 all over 18. The rate value is the k value, but converted to a percent. Okay, so you got to be a little bit careful here. Ln of 2 all over 18 is 12. Let's see how many decimals I want. Two decimals. So 12.48. That can't be right. It's divided by, sorry. So the k value is 0.0385 about. But that's not what you're going to put in for the annual rate. The annual rate, then, you have to convert it to a percent, and that would be 3.85%. Okay, but in the equation, just leave it as your k ln over 18 value. Let's go ahead and evaluate it then when t is 9. So after 9 years, what is the investment amount? To 2 decimals. Geez, really? Let's think about this. The doubling amount is 18 years. E to the ln 2. So there's no way. That's right. Oh, no wonder. Right, so that seems more reasonable. So always think about your solution. So the issue with my solution, it got too big. The doubling times only is 18 years, but this was they only want to know the amount after 9 years. So it shouldn't double. It should more than double, which is what I was seeing. It was way bigger than twice the original amount. So that was wrong. Okay, so this looks like $20,506.10 when I round to the second decimal. Yeah. Okay. So the video quiz this time, we'll make problem 44 from the homework. And so you're beginning with an initial investment of $6,000. And they want to know the rate, the time to double, and they give you the amount after 10 years. Okay, so that's the quiz. You have to write out, find the answer, show work, just like the work I'm doing here in class. So your work should mirror the work I'm doing. So I'm presuming that you're watching the videos and all that stuff. If you decide to do things your own way, you're just going to make more work for me. And it's going to affect everybody. Okay, because I'm going to have to go, all right, did this guy cheat? And then spend a couple hours online looking for where you got your answers. and that will take away time from other important activities, which will, that will affect everybody. Okay, so please do it the way I teach you to do it. Don't do it your own way. The way I do it is pretty standard. There's not too many people that are going to be doing it differently. Okay. All right. Problem 12 and 13 then are on the Newton's law of cooling. So Newton's law of cooling. Which basically says the change in temperature of an object is proportional to the difference between the temperature of the object and the temperature of the surrounding material. Okay? So the cool thing about differential equations is you'll get an idea of what the kind of concept is, and you could literally translate it into mathematical terms. And then solve it, and you'll have an equation that you can use to make predictions. Okay. All right, so there's our equation, and usually you see it in like a pizza problem scenario. So you have a pizza, you took it out of the oven, it's 300 degrees, and you put it in the waiting room. How long until you basically have to throw it in the trash because it'll get too cold to give it to your customer, right? So you can solve that with this kind of problem. Obviously, if you put the pizza in a very cold room, its rate of change of temperature is going to be much quicker than if you put it in a room that's basically the same temperature as I don't know, as it is room temperature, like 70 degrees. So if you put it in a room that's like minus 30 degrees, it's going to cool much quicker than if you put it in a room that's 70 degrees. Let's look at number 13. The answer is always a little bit tricky. And this, it's not a hard problem, it's just a little tricky. Okay. So our differential equation, we want to solve this guy in order to get our formula. The T sub m thing, this is the temperature of the surrounding area. So let's read the problem. Okay. So a container of hot liquid is placed in a freezer that is kept at a constant temperature of 20 degrees. So T sub m is going to be your 20. The initial temperature of the liquid is 140 degrees. So they're giving you some information, like in the chart problem, where they give you a couple bits of information, then you're able to solve for C and K. Right? So here they're telling us when T is 0, the temperature is 140, and then they go on to say when we get the time 5, the temperature becomes 60. It cools down to 60 degrees. They want to know how much longer after it cools down to 60 degrees will it decrease to 30 degrees. Okay. So they're not looking for T here. So to solve this problem, we'll find the T value, how long it takes for the temperature to decrease to 30 degrees. But that's not the answer they want. They want the difference between how long it took to decrease to 60 degrees and how long it then after that to decrease to 30 degrees. Right? Okay. So anyways, first we need that standard equation. Like previously, we already knew the equation for exponential growth that would result from the differential equation for population growth or decay. We kind of already solved that several times, and we found it was y equals c to the kt. But now we need to figure out what this equation is. All right, so what I do is separate. I'm going to divide both sides by that t minus 20, multiply both sides by the dt, little dt, integrate both sides. On the left, you can do a u sub if you wish for the denominator. Okay, so I have the integral of du over u. On the right, you can go ahead and integrate that. Integral of du over u is the natural log of the absolute value of u. Let's back sub the t minus 20. And then we want to go ahead and exponentiate both sides. So we'll have ln of the absolute value of t minus 20 equals e to the kt times e to the c. Okay. I need to get rid of that. Whoops, I didn't get rid of the ln, sorry. I need to get rid of the absolute value, so drop that, replace with plus or minus, and then replace this thing with a constant. There are restrictions on some of these values, but we can kind of proceed in this way. We'll get the answer correctly. Then I'm going to move the 20 over. So I have c e to the kt plus 20. So it's a lot like the exponential growth equation. And actually, you see it right there. You know, but then you have to tack on the room temperature. Okay, so anyways, I need to figure out what is C, what is K, so I go back to this initial information and figure that out. Okay, so when little t is 0, big T is 140. Move the 20 over, I get 120 equals C. So my equation now is 120 e to the kt plus 20. Now use the other piece of information. Big T is 60 when little t is 5. Divide both sides by 120, that'll be 1/3. Natural log both sides. Divide by 5. And so our final equation that we can use to answer the questions, t equals 120 e to the t ln 1/3 all over 5 plus 20. And now they want to know what the heck is little t. So how much longer will it take for the temperature? So we just want to find first the time it takes to reach 30, and then we'll determine the time it took from the temperature to get to 60 degrees to the temperature to get to 30 degrees. Okay, so I'll have 30 equals 120 e, and I'm solving this time for t. Move the 20 over. Divide by 120, get 1/12. Take natural logs on both sides. Finally solve. And we want 2 decimals for our approximation eventually. So it looks like approximately 11.31. Okay. So that's the total time to go from the initial temperature of 140 to the temperature 30. Okay, we want to know how long it takes to go from T equals 60 to T equals 30. Okay. So the temperature from 140 to 30 is 11.31. The time it takes to go from 140 to 60 was 5 minutes. And that's right here. So all you have to do is subtract 11.31, take away the 5 minutes it took to get to 60 initially, and you should have your answer. 6.31 minutes, probably. Okay, okay. So thank you for watching, and I'll see you next time.